In this video, we will look at the most common and difficult type of questions in Maclaurin series, proving of higher order differential equations given a certain function. When given complex equations, it is very tedious to perform repeated differentiation using direct differentiation methods. Thus, we can differentiate and express higher order derivatives as differential equations that consist of x, y, and lower order derivatives in order to reduce the complexity. For example, we can have the equation y equals to e to the power of 3 tangent inverse x, and if we were to find the second order derivative through direct differentiation, we will get this as dy dx, and subsequently this as the 2y over dx square. We can imagine that it will be a very tedious task to perform further differentiation from here onwards. However, if we try to manipulate the equation and differentiate using implicit differentiation, we will get this equation as the first order derivative and this equation as the second order differential equation, which will be much easier to differentiate from this second order ODE as compared to the earlier d2y over dx square. The tough part now is to be able to move from the original equation into the one that we are required to show. We will make use of the next few examples to illustrate some tips for proving these equations. To 0, and I have shown this equation. The second trick is to make use of inverse trigo functions rather than trigo functions. This is because whenever we have trigo functions, no matter how many times we differentiate the function, we will still end up with a trigo term. And this is not the case when we have inverse trigo functions. Thus, let's look at y equals to tangent of ex minus 1. We need to show that it is going to be this equation where there is no trigo term at all. So I know I do not want to work with any trigo terms inside my original expression before I differentiate. And I'm going to change this into tangent inverse y equals to ex minus 1. And now I can perform implicit differentiation to get 1 over 1 plus y square dy over dx equals to ex. Now, we can make use of the first trick that we learned to cross multiply the 1 plus y square across, and we can perform product rule rather than performing a quotient rule. So this becomes dy over dx equals to ex times 1 plus y square. And I shall call this equation star for now. Next, I can differentiate this equation, and it will give me the 2y over dx square equals to ex times 2y dy over dx plus ex times 1 plus y square. And what I can see is this term is the same as the right hand side of my equation star, and therefore I can simply change it into dy over dx, and I will get ex times 2y dy over dx plus dy over dx. Now there is a common dy dx term on both sides, which I can factorize. So I have dy dx multiplied by 1 plus 2ex times y, which is what they have required me to show. The third trick is to remove roots on both sides by taking the power on both sides. And the reason for doing so is because whenever we have roots, by performing chain rule to differentiate it, the term actually becomes quite complicated. So if we can remove the roots, we will simplify the differentiation process slightly. And if we have y equals to square root of cosine x, what we have to do is to change it into y square equals to cosine x, and I'm going to differentiate it implicitly now. And this gives me 2y dy over dx equals to negative sine x. Let's differentiate it again. I will get 2y d2y over dx square plus 2 dy dx times dy dx equals to negative cosine x. And note that cosine x can be changed into y square since we know that y square is equals to cosine x. Therefore, the right hand side of this equation becomes negative y square. Now, I just have to bring everything to the left hand side and simplify the equation. And I will arrive at 2y d2y over dx square plus 2 times of dy dx square plus y square equals to 0. And this is the equation I'm required to show.